All right, guys, let's get the lecture started. So today we'll be talking about most of the content that we covered in the second half of lecture, which is also going to be the main part that we tested on the exam 2, which is tomorrow. So before that, we posted the homework 7 solution on the course website. So make sure you check that out. A lot of the questions will look similar to previous exams, but also to the homework. And exam 2, if you still remember where you sit last time, go to the same exact room, and then you will you'll be assigned similarly as the exam 1. For folks who start earlier, the 3115 will be the room that you go to. If you start earlier than 3:30, we will email you a different room number for that. If you believe you have a SSD accommodations or you need to have any alternate times for the exam and haven't received the email from either me or James, please email us as soon as possible. I think we should already reached out to everyone who have the SSD accommodation request. But if not, email us soon. Similar as the exam 1, we will post the data sheet today after class. So make sure to go through them. The data sheet is about the same length as the exam. So make sure you take time to read it before you go into the exam. And we will have open lab today right after lecture and also tomorrow morning for any questions that you need. Aside of that, we will have the student presentation next Thursday. The attendance will be requested. So basically, you will be each submitting like a score-ish to each of the student presentation that will count towards your class attendance or class participation. We will post that link every time in the lecture with a URI, like a QR code. We will talk about that a bit later after the exam via Piazza. But like we said last time, schedule a 30-minute slot with us. The whole presentation is about 12 minutes plus a few minutes of Q&As from the class, so about 15 minutes, give or take, per team. We have already been working on the assignment. I think we're almost finished, but we will probably release that after the exam so that you don't get distracted. So the logistics, very similar to before. Closed book notes, the calculators, only the normal calculators, no graphics, and the clock timer will be provided. One thing I would like to add to this is think about the exam as like a 50-50 division. The 50% goes to everything before the design question, 50% goes to the design question. So you were facing a slightly longer design question than last time. Make sure you save at least like 50 minutes for it. So another thing is we designed the design. Let me just also get this out. We designed the design questions so that each of the individual questions can be answered individually. So you don't have to necessarily figure out the current question in order to work on the next one. So if you got stuck on one of them, you can jump to the next one to work on that. It's possible that the next one is easier than the previous one. So, and all these strategies that I'm sure you guys already know. Yeah.
Will we be expected to write any code for the design question? I don't know if that's a question you can answer.
Yes, you will be expected to write some like C code in the exam. On the data sheet, I think you see in the previous data sheet that we sent out, we have some like standard C library references included in the sheet. So you should have everything you need, and we will not be super strict on the syntax. Make sure you have the address right, the values right, the value usually corresponding to which mode each thing needs to be assigned. Is it active high, active low? Make sure you have these correct, and we don't check indent though. We don't check how many space you put, just like C code. Any other questions? Okay, cool. And for the data sheet, like we said, we'll be released after class today. Make sure if you see anything that seems confusing to you, either come to the open lab or post on the Piazza so that the entire class can share. We will possibly update the data sheet based on the feedback we got from you guys. So we might add more details to this, but before the one you get during the exam will be the most updated one. We'll print that out to you, and any changes we make will be posted on the Piazza. So, any questions regarding the data sheet? Okay. What to study. Old midterms will be the best things to start. Get familiar with how a design question feels, how the entire build-up and how many questions you roughly will be facing. The structure of the exam will be quite similar to the practice exam, namely the exam from last year this time. And yeah, save time for the design question. We recommend 50-50 division. Topics to be covered, technically everything in the class so far in general, but everything on the top, which is covered in the previous half of the lecture, will be shown up only in multiple choices. And the midterm 2 will be more focused on the interrupts, timers, serial communication protocols, as well as analog signals, ADCs and DACs. But again, not a complete list, just a starting point. We will still have a little bit of those basic like electronic circuit stuff here and there, pull up resistors, pull down resistors, etc. Make sure you have no short circuits and all that. But they will be more like blended into the questions. Any questions regarding the topics? I think I see the Piazza post, someone asked about the lecture coverage. So technically everything, but largely focused on the second part. For the first part, you will likely only see them in the multiple choices. Any questions? Okay, cool. So let's start with the interrupts. Again, this figure, you guys have been quite familiar with this so far, hopefully. The interrupts does not use the traditional, like the normal HVB buses that everyone else uses. It have its own line directly connects back to the core. And that thing technically goes to a component called MVIC that basically handles all these interrupts. It determines whether, which interrupt is currently pending, which one should be active, or which one should go next, based on how many ever interrupts it's currently in the queue. And just to give you like a quick overview of the how everything happens, some type of external interrupt occurs, usually on the rising edge, and then that goes through a peripherals, in this case a GPIO pings, but all the peripherals have a designated interrupt index. And that signal goes to the MVIC, and that usually corresponding to an index number. In this case, it happens to be 9. So there is a interrupt request number or interrupt request index associated with each of the interrupts. And you will calculate the memory address containing the location of this interrupt request handler function. It's this is the formula there. 64 times plus 4 times 9. 4 is because 4 bytes. It's all 32 bits per register. And then after that, the address will be retrieved from the memory containing the handler functions, and that got feed into the core. Feed into the core if this is the term for this interrupt to be executed. If we look at from the other angle, different MVICs coming in, points to an index, and then that goes to an address to find the actual function, and then they will, where were we? And that function on the top will be fed into the core for the execution in next steps. From like a very high level, this workflow is clear to everyone. How the interrupts request is triggered, and then what does the MVIC does, and to find the interrupt handler functions in the memory, and then pull that to fetch that to the CPU. Yeah.
I just have a quick clarification. I know that the NVIC has pending bits for each interrupt number, but then doesn't, at least on STM32, like the GPIO external interrupt, doesn't that also have its own pending state? I recall hearing that.
GPIO pings pending state for like a buffer, or?
Like that I don't know, maybe I'm misremembering something, but I remember the peripheral itself having a separate.
It's possible that different peripherals have its own configurations, but generally, whether this signal coming that triggers a interrupt is decided by the programmer. So, depends on the signal. The programmer usually set it to be either have a valid interrupt or not. Yeah. Any other questions regarding this? Yeah.
Where is external interrupts priority handled?
Oh, yeah, that's what's going to happen next. So, yeah. So this is just if there is only one interrupt occurring. And just give you one more example on the simple cases with just one interrupt hanging there. The program was executing its normal stuff, and then there's an interrupt signal occurring, and then the hardware does a stacking and then take all of these registers into the stack, and then it goes to the interrupt handler function, and then after that's been finished, it does the exiting, and then we do the unstacking, which is also again handled by the hardware, and go back to the main program. This is the typical workflow look like from the CPU's perspective, or like from the core's perspective. And when we have, just to put it in Word, the signals determine which interrupts to proceed, and then the registers to go to the stack are the program counter, PCR, the stack pointer register, the R0 to R3, which are the registers that are used to take the input for the handler function, and also where you put the return value to the handler function. And then also the link registers, and R12, which is where you store the intermediate values if needed. And the address will be fetched to the core and then executed, just like we showed before. We have, I think one classmate just mentioned, when we have multiple interrupts happening or triggering, what happens is that it's going to be executed in its priority, and the smaller number means higher priority. Remember, there are some system level interrupts from the core, or some system level warnings. They actually have negative number of the priority. So those things basically means you can't really overwrite, except for usually you can't overwrite, except for there are two special registers you can use to override those. But we're not going to test on that. So smaller numbers means higher priority for majority of the case. And this is for deal with the concurrent, if you have multiple waiting in line, but also can do with the overlapping interrupts, meaning you have an interrupt that's currently under executing. If you have a higher priority interrupts coming in, you could amp that existing interrupt and then executing the higher priority interrupt first, and then go back. The three cases we talked about are preemption, tail chaining, and late arrivals. If we have all the pending bits and enable bits, active bits taken in consideration here, the top part is the hardware, the bottom part is the software, and this is the single interrupt case when there is no conflicting or no interrupts that's getting in the way. So basically, in this case, there is this one interrupt coming in, and then that's the pending, that raises the pending flag on the pending register. That will also update the base priority register value currently to the current priority of the interrupt, which is the 6, the index 4, because we count from this way to that. And that will then trigger and all those interrupts are enabled. So if the pending is up, that means this interrupt is it can be executed or should be executed, and that will also trigger this stacking on hardware. Basically, all of those values that we mentioned before will go pushed onto the stack, and then that will also make the active bit up. The active bit up triggers the pending bit to go down. And then after the execution of this current handler function, the program will exit from the current handler function and back to the main program, which will trigger another unstacking. And that unstacking will happen concurrent with the active bit going down to go back to the main function. So this is the simple case, the most straightforward case with no conflict or concurrent interrupts. Then we talk about preemption. So basically what happened is while we are executing a lower priority interrupts, which in this case is the same interrupts we were showing in the previous slides with a base priority of 6. And all of a sudden, there's another priority happens on the index 3, which has a priority number of, happens to also be 3, which is higher than the base priority of the current interrupt. So that will amp the current interrupt handler function, does another stacking. So on the stack, you will have 2 set of the value from the same group from the group of the registers that's supposed to go onto the stack during the interrupts. And then the active bit is on for this index 3 interrupt. And because the index 4 interrupt was being amped during this process, so the active bit for that is also on. So we could have more than one active interrupt. And then the system the core goes to execute the higher priority interrupt handler function. And after that, it's similar to before. It first does 1 on stack, and then it does finish up the rest of the interrupt request 4, and then does another on stack, and goes back to, after that goes back to the main program. Is the preemption, is the interrupt preemption case clear to everyone? Yeah.
With the pending bit will be set to 0 will be clarified questions. Otherwise, we are thinking that it is cleared before the ISR is executed.
The pending will happen after the active bit's up, and then that triggers the pending bits to go down.
So the pending bit is cleared before the ISR executes after the stack.
It's after the stacking, yeah. So you will stack, and then it became active, and then it pulls down the pending bit on that same request. Yes.
Yeah, so what is the scenario when the pending bit and the active bit are 1 at the same time?
There shouldn't be that. So as soon as the active goes on that one, if there's only 1 interrupt request, and then that means that will pull down the pending. But it is possible that while executing that same interrupt, there's another external trigger, meaning that same peripherals could raise another interrupt. So if there are 2 interrupt requests from the peripheral, then that's the case, and that happens during that interrupt is being active. Then that's possible that we have both of them on 1.
So it has, you have to have an interrupt that's executing and then preemption happens. And
On that one, it won't be the preemption because they have the same priority. Imagine if say on the, imagine here, this interrupt index 3, it's a periodic happening, and it just happens to be 1 at this stage. On the peripheral side, it determined to do another read or another interrupt from the peripheral. So the peripheral send another interrupt request to the NVIC. So on NVIC, it will put that pending bit up, although that interrupt is currently being executing.
it's just
Yeah.
being multiple.
Yes, but if there's only 1 request, then they usually they will not be on at the same time. If you have multiple on the way. for the same interrupts. Yeah.
So what happens if a higher priority interrupt like becomes active, or sorry, becomes pending during stacking or during unstacking? Will the stacking or unstacking complete before like the preemption occurs, or will it be interrupted itself?
Great question. So we have one case for that. Actually, it's the late arrival. So if during the stacking that happens, it still amped the lower priority interrupts, because that interrupt has not get executed yet. So the registers, like PC link registers R0 to R3, they're still clean. So they haven't been used by this lower priority interrupt. Yeah. Any other questions regarding this case? Okay, so the tail chaining, which is usually the easier or like most straightforward case, means like there's same or lower importance interrupts occurs while the core or CPU is handling the interrupts with the same or higher priority. Basically, it just means that interrupts will stay in the pending and wait until the current higher or the same priority interrupts finishes. One thing to note is that it will not do another stacking on stacking, to save some operating time. So put it onto this nice timeline again. Where you have the index 1 interrupts being triggered, and that means during the execution of the index 4 interrupts, which has a higher priority, which is 6. Higher than 10. So the current interrupt still gets to keep executing. However, it trying to go back to the main program, it knows that there's another interrupt already pending there. So it will not do the unstacking from the stack. It will directly go into executing the next interrupt in line, waiting in line. And then after that, it will also, just like before, have the base priority updated to the current interrupts priority, as well as have the active bit on for the corresponding interrupt. And after that, they do one unstacking and then go back to the main program. This is clear. And the late arrival basically, it happens during the stacking. There's a higher priority coming, so it still do stacking, but just do one stacking instead of do 2 of them. Yeah.
So in the case of late arrival, since for the lower priority interrupt, if we haven't branched to it yet and then we go to the higher priority one, would the lower priority one only go from pending to active later probably?
Yeah. So any questions regarding the interrupts? Sorry, I think I forgot to put the late arrival slides here, but it's in the previous lecture. So if you're a little bit unsure, feel free to check out the earlier slides. Okay, so we next go to the timer. Timer is one of the very essential, essential portion of the embedded system or computer in general, because that's one thing that the computer and embedded systems does really well and really cheaply. And to just give you a high overview, first we have the clocking. You have a prescaler to usually scale down the fast clock before you feed into a time counter. And this time counter will be linked to like a ARR, auto reload register. You usually have a number that you can set, and whenever it reaches that number, it triggers a ISR interrupt. And we also have a compare and capture register, the CCR. It will handle the input from the GPIO if it's in the, for example, in the capture mode. If that comes in and it compares the value with the whatever value you set. If they match or don't match, depends on who set it. It can also trigger a interrupt. So the value will be it will be compared with the counter value that's been counted towards. One thing to notice when you do the calculation, make sure you remember to add 1 to the prescaler. This is a whatever prescaler value you set, you will add 1 and then use the clock to divide that. That's a system protection so that none of the divide 0 will occur during any type of configuration. So it's possible that your prescatter value ends with a 9 or a 99 or whatsoever. One like a specific external event happens, such as like I think in this case, rising edge of a external signal on a GPIO pings, the hardware automatically will take that data and the current value as well as the current value of the timer counter, and then we will compare those two values and to see if any interrupts needs to be triggered. This is the capture mode for the CCR, the capture and compare register. For the compare mode, just put it out. When the timer 2 it's usually used for like an output mode. So the capture mode usually used for input mode. Compare mode usually used for like an output mode. This is when like timer is configured to generate a output signal. The hardware will essentially consistently compare the free running time counter's value as well as the value that's stored in the CCR register that's set by the programmer in the compare mode. And whenever the two value equals, then that would trigger a interrupt that usually corresponding to like an output signal. You can think you set a number, and it could be like a periodic signals that you're trying to generate. Usually, used for PWM signals, but it can also be used for if you just want to, I don't know, switch on and off a LED for whatever reason. So yeah, this is just another view from for the CCR. And for the counters specifically, it have multiple. You have different ways of counting. You can do a count up or counting down, as well as the counting up and down. In this case, you essentially get double the amount of the bits the double amount of value you are able to count based on the same amount of bits you have. Yeah, you can set however you want it. Just make sure you stated your configurations or assumptions. We will, any questions we asking about this, we will also tell you which mode it is in. If we don't tell you, make sure you just write it down, like what's your current configuration on that. Yeah.
I guess if you're in compare mode, and you're just trying to, say, measure a specific duration, why would you need ARR?
Why would you need AR? Good question. So remember, like in the PWM signal, you have the period and you have the duty cycle, right? So you can think like the ARR would be the period that you are setting. So the entire signal goes to, I guess if you set it to be, say, 10 milliseconds, then that's like 100 hertz signal from the top, like 100 hertz signal, right? And then the compare value set in the CCR will be essentially determine the duty cycle of that signal. So how many percentage of that should be high or low? So
yeah, I guess I meant in the case where you were using compare mode but not implementing PWM.
not implementing PWM.
To measure a one-shot duration, wouldn't you not really care about ARR?
Do you mean still for generating output, or? It's usually used for the output. Yeah, it's usually used for the output. So you can think like the ARR is the ARR and the frequency of the clock that go into the time counter. They together determines the period or the period of the generated signal from this configuration, and the value stored in the compare and capture register in the compare mode. That determines the duty cycle, essentially, of the signal. You can set whether, or you can also, but you can set whether the signal should be high or low on either of, if say you have the ARR to be 10 and then the compare value to be 7, So you could set everything above 7 to be 1, everything below 7 to be 0, or you can also set everything above 7 to be 0, and everything below 7 to be 1. So you have this freedom of set however you want on the 0 and logic 1s and logic 0. Yeah.
So for compare, is it like it'll generate the PWM signal on the OC ref and then also de-interrupt whenever they're equal? Like if they're two separate things it does?
Wait, can you say one more time?
Like for the compare mode, one thing is that the PWM mode, it generates that output signal that goes up and down depending on the comparison. And then does it just also generate the interrupt when the two values are equal?
That's a very good question. So you'll see that there are two interrupts there, right? The top interrupts essentially determines the overall signal, like the period. You need the signal to determine the large period. It might look strange here because, why do you need two interrupts to generate a signal, right? But in reality, one of the time counter connects to multiple of the CCR. So each CCR can have its own compare value stored there. So essentially you have, say, the same period signal, but you can generate a duty cycle of 50%, 20%, 70%, and that all uses the same time counter. Yeah.
I guess what I was wondering was like the lower ISR of the two, that would not actually be used to generate the PWM signal, right? Like the PWM signal gets generated directly, and then the ISR is in case you want to do something else with it?
That is actually for the PWM signal. So this will determine exactly how many percent is high or low. So the top one decide what the signal looks from like a higher perspective, and the lower one determine within this one period how many percentage of time is corresponding to a logic high, how many percentage of time is corresponding to a logic low. Hope that explain it. Yeah. So they work together to generate PWM signal, which is one of the most commonly used case for the compare mode. And yeah, this is kind of similar to what we just talked about. You have essentially a cutoff. So each of this triangle, it's like, let me see. This length is determined by the AR, and whether that blue line, the height of that blue line, is determined by the compare value you put in the CCR. And you could have multiple blue lines using the same, the signal of this counter. So you can essentially have another signal that looks like essentially wider than this or narrower than this. And they together corresponding to an average output value at a different level. So the duty cycle, when we generate fast enough, it will kind of work like AC signal, but it's above the 0, and that gives you a equilibrium voltage DC voltage output. So if the frequency is fast enough, this is the equilibrium DC output from the device that connected to. We good on this part? What each of the registers being used? Yeah. The what?
Repetition counter register.
Oh, the repetition counter register, it's a register that set whether you generate, like how many times you generate each of this periodic signal. If it's 0, then it just always generates. So it's like a continuous mode. The other number tells you if you generate once or generate twice. Yeah. Yeah.
Yeah. She asked about it, but I just wanted to be sure. So on the capture mode, the interrupt that's generated when they're actually equal, I could only see it being useful on like the event queue thing, or like when it actually matches, then you will be like, oh, okay, they're actually equal, so I act upon it and change the order of the event queue. I couldn't, and I thought I couldn't see it being useful on the PWM.
Oh, you mean for this mode, the capture mode, or for the compare mode?
Yeah.
Still for the compare mode. Wait, sorry. Capture or compare? Compare. Okay. Yeah. Yes. Can you say the question one more time?
The compare.
Yeah.
I couldn't see So the output compare register enable.
Is for the output, yes.
Yeah, right. The interrupt wouldn't be doing anything in that case, right? I could only see the interrupt being used for like the event queue and other stuff, not on the WNS.
The interrupt will control whether to set the output pin to 1 or 0. To set the output pin to be 1 or 0.
Wouldn't it be too slow to do that? Because like the ISR would take so many cycles to do the process.
Would it be too slow to do that? So the configuration period will be a bit slow. But once you finish that part, it will keep running on its own. So you will see that every time you should, that's also the reason why you wouldn't want to change the ARR value too much, because that actually take time to do, because that corresponding to a actual clock that connects to it. But once the clock is set it up with the ARRs and counters, the counter counts on its own. It doesn't take the CPU or core's attention to do that, because it's a separate piece of hardware. It's implemented on hardware, so it doesn't interrupt with, let me stop using interrupt. It doesn't occupy the computation power from the core. It's running on its own clock and its own registers. Yeah.
Yeah. So in that case, that's right. They could use the interrupt to set the OCREF.
Mm-hmm.
So then, imagining an upcounting thing.
Yeah.
The act of reloading would also need to generate an interrupt so that it cleans the OCREF, right? Because when it reaches the
It will,
6,
yes.
Okay, so it would also have its own.
Yes. So that will be corresponding to what essentially see the top peak and then drop down. So that corresponding to the period of the signal.
Has another interrupt there.
Yeah, but also that part is also being handled by the hardware. So, within.
The interrupt to reload. Yeah, I think. Yeah.
So the bottom line is, you have the ARR value, and then whenever you count to that value, it automatically goes back. So the interrupt for that one, what it does is super straightforward. It just reset the value on the current counter. It doesn't do. I don't think it does anything else. So it's a very, very quick thing, and it's working on its own. So on its own hardware. So it does not take from the CPU or core's computation power. We good? Okay, perfect. And then next we move to the serial communications. A few serial communication protocols we talked about. First is the non-serial or parallel communication. There are some good and bad about this. The main good part is it's super fast. So usually when you connect them, it's connected bit by bit. So if you have some, usually this is used for within the chip communication. It is also possible sometimes to be used for off-the-chip communications, meaning if the component has a bit-to-bit output and that needs super high speed to talk to the core, it's also possible to have that as a parallel communication. Just depends on how the chip is set. And other downside of this, the good side about this is just super fast. So if you see a super fast components needs to be communicated, you can also think about parallel. If the downside for this, it's very expensive in terms of the wiring. Chances are the thing we interrupt with are 10 bits or even higher with most of the resolutions, bits resolutions. So that alone will cost 10 wires, which is usually not ideal for the between chip communications. So this is non-serial. It's the parallel communication. Under the serial communication, we have this UART, which is super straightforward. They have 2 wires, TX and RX, transit and receive. And the TX of the device 1 connects to the RX of the device 1. The TX of device 2 connects to the RX of the device 1. So it's a four duplex communication. They can happen at the same time, and they share a ground. They do not share a clock, and the clock goes down by essentially oversampling on each device under a agreed communication speed, usually sometimes called baud rate. If you work with Arduino IDE before, there's a baud rate you can set when talking to different microcontrollers through Arduino. Yeah, and we talked about how the clock is possible. Usually it has like a parity bit attached on the back, on the end that basically tells you whether it's an even number or odd number of zeros in the data, and that can give you like a good, very cheap way to check the data integrity on your receiving side. You could configure the data to be 5, 6, 7, or 8-bit, convenient the 8-bit corresponding to the ASCII number. So most of the strings, numbers, characters can be covered with just 8-bit of data. And this is also it has a start bit and a stop bit, so that it knows whether there is something on the bus right now. Yeah.
About the oversampling itself, because like, for example, the 10% that we have there, that drift, it's only caused by the difference on the baud rate, right? Because that's the only thing that caused the drift. The oversampling, it would only to have like the detection of the edge happen as close as possible as to the edge happening itself.
Yeah, technically on a well-implemented one, the difference should only be that, yes.
Yeah, right?
Yeah.
So like if you have 16 times, then it will be 1/16
Mhm,
max.
yeah.
So, but it doesn't alter the drift caused by, right? Like the 10% or something. It just adds an offset that will be in every single one after that. So we want to minimize it so that the offset wouldn't like.
Yes, so it's true that there is essentially a unavoidable error between however fast you oversample. There could be a shift on one clock cycle, right? Which is why under the oversampling, it always sample in the middle. So if I sample 10 times faster than the signal coming in, the actual sample of data, like you log the data on the cycle 5 to give actual wiggle rooms or actual tolerance if the signal somehow got shifted a bit on this. And that's generally enough because every time you essentially only send 10 bits of data, give or take. So the next data comes in will be another calibrating of this. So usually although it's possible that there are some accumulated error, but that usually don't affect because it's only this much of bit, and then we oversample it so much faster. Yeah.
But that's another thing that I was thinking, because like I understand that we would sample it at the middle,
Yeah.
right? Because then it's more stable there. But the fact that we sample it at the middle, right? Because the total error, it will be like the initial error from like how much after the edge itself that we started, plus like n times the drift caused by the difference in baud rates.
Yes.
Right?
Yeah.
But it's also plus the 50%, because we start at the middle. So like it's at the middle and then plus 5, 5, 5, 5, 5. So like if we have 8 bits.
Oh, it's plus 10, 10, 10, 10.
Yeah.
Yeah, so it's always at supposedly the middle.
If we, like I'm saying, like if we did before the mid bit, we could have like a more, like a longer string of bits, assuming that like the signal is stable enough. Did you understand what I'm saying?
You're saying like there are accumulated error between
Yeah,
each?
like, for example, they say that the max drift
Uh-huh.
is advisable is like 5%
Yeah.
per each bit. So that if like, since we have 8 plus 1 from the start, so it's like 9 plus 5, 45, so it's like 50% plus 45%. So like the phase shift, the worst case one, at the last detection thing that we have is at like 95%. So it's almost at the other.
I see what you mean. Okay,
Why,
so.
why do we have it at 50 and not sooner? Because then we have more bits.
Okay, so usually in real life, when we have this shifting, it's usually plus and minus. So it's very, very, very rare that they all accumulate in one direction. That's one thing. And second, when they say it's how many percent tolerance, right? That's already a little bit over the extreme case. So if, say, in the end, you only have 95%, that's already well enough for this communication protocol. As long as this, yeah, the 95% you can consider as theoretically the worst case. Accumulated together, that's 95, which is still below 100%. So we should be good on that case. Yeah.
Go the other way, so like
Yeah.
the middle is the best.
Yeah, yes. Okay, and yeah, this is just another sample signal looks from a oscilloscope's perspective. And for the SPI, we have essentially 4 wires, and the SDO and SDI, the serial data out, serial data in, are the shared buses within between all these peripherals that connects to the controller. So it's one controller to multiple peripherals type of communication. SDI, SDO, it's always stated from the perspective of the device. So you can you might also hear master in, slave out, master out, slave in pings. These are essentially the same thing. You can think of the controller as the master device, and then the peripheral device as the slave device, because it's one to many communication. And one thing is that the CS ping, the chip select ping, is 1 per peripheral. So if you need to add more peripherals or more devices to this SPI protocol, you essentially add one extra wire per device, which is the chip select. And every time when we talk about how many wires you need for the communication, we don't count the power and the ground. Also, yeah, the chip select ping is flipped. So it's, when it's with the low, it's actually higher. So it's an active low, so to speak. And the controller will be the one who generates the clock. And this is the clock phase and polarity. It might look a bit confusing. This is usually due to the historic reasons, because SPI is this quite flexible communication protocol. So every manufacturers can, actually they did determine their own configuration details. So basically, the polarity, the C polarity, basically means whether the clock is idle high or idle low. So maybe the next figure is a little bit clear. So if when there's nothing happen, if you look at S clock, if it's high, that just means it's idle high. If it's low, for example, like the top 2, that's idle low. So that means the clock polarity is 0. And the bottom 2, the S clock was high, which means the clock polarity is 1 for that case. And the clock phase basically means whether the actual data sampling happens on the rising edge or on the falling edge. So the rising edge is, so basically just make sure you know this, and it's not very complicated. Just make sure you know which polarity corresponding to which, and they don't necessarily have to interconnect with each other. Yeah.
How does a peripheral, on previous slide, how does a peripheral generate interrupt?
How is the peripheral generating interrupt?
Can it generate interrupts?
It can. It's usually generates through the controller. So the signal goes to the controller, and then the controller, the interrupt generated from there to go back to the core. Yes, and the peripherals that connected essentially chip to chip, that they don't directly talk to the core for the interrupt. Yeah. And like a tip, like we're clear on this, like what 0 and 1 means, and how do you? Okay, it might be a little bit confusing, but just remember, what each means, and that should should be good. This is like a typical SPI transactions. The select ping will be low for the selected peripheral. So, and the SDI, SDO, SDI, they technically can happen at the same time, but depends on whether the controller is actually expecting any any input from the peripherals. You can just ignore the data from there. And similar to, this is like a pretty standard, configuration which samples on the rising edge. So this just gives the value corresponded to that signal. This is also full duplex because it have the separated data line, so they can happen at the same time, similar to the UART. And then we also have the I2C. This one is each device have its own unique address. This one is half duplex. Reason for that is they share a SDA serial data line, and that data line every time it can only have essentially one value on them. So it can either do a signal, like a data sent from controller to a peripheral, or receiving a signal from a peripheral. But this one can do multiple controllers and multiple peripherals. The one broadcasting, when multiple controllers trying to broadcast to the SDA, whoever gets to 0 wins the SDA bus. So if it's kind of odd way to do it, but if you think more about it, it actually works, and it doesn't add any additional lines. And one other thing is you do need to add a pull-up registers to the 2-line. This is so that none of the device, either controller or peripherals, would be able to pull up the controller, like the SDA line. So imagine if you have 2 devices trying to pull up, meaning give a logic 1 to that line, that will cause a short circuit, which is not good. So all the device, controller or peripherals, will only be able to pull down the line. That is also why whoever gets the 0 first will win the battle. And this is essentially the normal speed, low speed, standard speed, and fast mode you can expect it from a I2C. So it's reasonably fast, not as fast as SPI, and way slower than the parallel. So the SPI usually you can think of it at like a magnitude of 10 times or so faster than the I2C. And the speed was corresponding to the value of the resistor, the pull-up resistor you put there. And the reason for that, let me just see. So the reason for that is essentially it takes different amount of time for the signal to reach a read valid high or valid low stage, usually valid high. So if you have a signal that's pull up or pull down too fast or too slow, usually too slow is the issue, it's likely you have something to do with the resistor values. And both of them are implemented, like we just said, as open drain, and then you need to put a pull-up resistor on that. And for the for like another diagram here, we have the starting condition, meaning we have like a high to low transaction on the SDA. One, the SCO is high. When both of them are high, that means the current bus is clear. And whoever pulls that SDA pin down, they will be able to start claiming the bus. And if there are multiple people doing the same thing, they just keep doing that, and whoever does the 0 first win the bus. This is another, yeah.
So the data is sampled not on one of the edges, but actually in the middle of the clock period?
So I think it's usually on the rising edge, but yeah. Yeah. Any other questions regarding this? this is like a summary between them. The wires you need, again, we don't count the ground and the ground and the power pins. For the UART, is 2 wires, RX and TX. The speed is usually slower. It's asynchronized because they don't have a clock to be shared between. It's 1-to-1, and it's quite simple to do. It's usually good for long distance communication. If you have like cables that are long, it's usually good to use this so that like any of the distortion or attenuation of the signals can be easier handled. It's also pretty good with the environmental noise because it doesn't have a high-speed signal that goes inside of the protocol. The clock, will be usually easier to be disturbed by the noise because it's the faster signal, and it's supposed to be a perfect square wave. For the SPI, it's 3 plus N. Any more you add, it's just 1 chip selecting. The speed is pretty high. This is all in like bits per second. It's about 10 times faster than I2C, 100 times about the UART. And we do have the clock signal needed, and it's 1 to N. And for the I2C, just 2 wires. You can have multiple devices, including controllers and also completers. So it's an end-to-end communication. You can also configure it as 1 to N, just depending on how you configure it. And it needs a clock signal. Speed is about 1 megabit per second. So if you're trying to calculate the speed you need, make sure you keep tracking how many devices has been connected. You have to count them together and then time them correctly so that you have a rough sense of what's the speed you're looking for that specific communication scenario. The one wire, it's one of the case that we talked about in class. It's usually even slower, and it's also asynchronized because there's only 1 wire, so there's nowhere to put a clock there. I don't think we test this, but it essentially can be implemented similar as the I2C, but with each internally agreed baud rate essentially. The parallel one, this is not serial. The parallel one is N for N bit, so 1 wire per bit. Depends on and it's usually for very high speed. So if anything that's, in the above 10 Mbit per second, then, or even in hundreds, then you should probably go with the parallel communication. And again, this is for bit per second. So if you have, say, multiple bits of the device that connect to this, you have time that by number of bits that you're expecting to come in. Yes?
If it's N for N bit and it needs a clock signal, how is that possible?
Oh, the clock, there will be like another line. Yeah.
Okay.
Yeah,
So,
yeah.
okay.
Yes. Sorry, yeah. So technically, another line for the clock. Clock signal will be needed. It's pretty simple, but expensive. Any questions regarding the serial communication protocols and 1 non-serial communication protocols here? We good? Okay, so then we have the ADCs and DACs. So a little bit on the digitalization. So it depends on how many bits you have. You will be dividing. This is essentially what you're doing with converting a continuous signal into a discrete signal. So essentially, you will have different steps to go between them. Depends on how many bits you have. In this case, we're 3 bits, and then this is the voltage range you have, say from 0 to 5, and each step will corresponding to a value. That's the resolution. You could calculate either way. There are multiple people asking during the class, whether we should do the -1 or we don't do the -1. In reality, it doesn't matter that much because chances are you're doing with 8 bit or 10 bit at least. So that little bit difference will not matter that much. In the exams, either way will give you credit. If you do 2 to the n or do 2 to the n minus 1, we'll all give you credit as long as you state it clearly. If you do 2 to the n plus 1, then Any questions regarding this? Okay, cool. So we talked about 3 types of different ADCs. The flash one, which, as the name indicates, super fast. It's pretty much a bunch of resistors connected in serial, and then they are very accurate to each other, easy to manufacture because chances are they're manufactured in one batch. So even though that R, say all the R's are supposed to be 1K, even though it's 990 ohms, but because they are fabricated in the one batch, chances are all of them are around 990. So it doesn't affect the performance of this that much. And each of the nodes basically corresponding to one step of the value. Yeah, and then we have like a comparator to check if the current value is higher or lower than the value on the input side, and then we can decide what's the closest value. And this is controlled. All these essentially switches or op amps are controlled by the like another encoder. So this is 3-bit. So there's like a 3-bit 3 to 8 encoder decoder there to extract the value mapped to each of the switch. For the single lobe, it's essentially converting an analog value into digital by measuring the time it takes for a capacitor to charge or discharge to the input voltage using like a constant current source. So it's not too many hardwares, so instead using the time. So it's quite easy or like quite cheap to calculate from the embedded system or CPU's perspective. We also have the star. It's kind of in the middle. It's basically using a DAC. Now that we talked about DAC, you guys all know what this means now. So basically, it's using the comparator circuit to compare the input analog signal to the voltage level that's being generated by the DAC, and then we will use like a binary search for the DAC value generated and find the closest match. So the worst case would be if we have like n-bit DAC or n-bit, which will also conveniently usually be the n-bit of the ADC. That n-bit will be the number of steps it needed to reach what's the value it needs to output in the worst case. So yeah, just start from the beginning and then go 1 bit at a time. Oops, sorry, 1 bit at a time. This is SAR. This also happens to be the ADC that's been used on our STM32 board. Pro and cons here all together. The resolution, flash is usually on the lower side because it's more costly to scale up. But if you only have if you only need a relative low resolution ADC, the flash is actually a very good option because it's fast, it's easy to fabricate, easy to manufacture, and very accurate. The slope integrator is also the resolution meaning it's able to support higher bits of the ADC easier because it's doing the time counting, which is something you can do with very high clock cycles, so very high resolutions essentially. Speed, very fast for the flash. The other two, the star is still fast, and the slope integrator is going to be slow because it takes a lot of cycles to do, especially if you want to go with higher bit resolutions. But for the flash, it's essentially just 1 clock. For the star, it's n clock essentially. Yeah. Any questions regarding these 3? Okay, and we talked about 4 different types of DACs. We have the PWM plus the low-pass filter, the resistance voltage divider DAC, which is very similar to the flash ADC that we talked about, but reversed. We also have the R2R ladder. It's convenient and built that each of the node, if you can see my cursor, each of the node here will split the current by half. Because if you just add up the resistors, anything under will happens to be the same value as whatever directly connects to this. So it's always divided by half, half, half. And we also talk about the binary weighted resistor DAC. It's essentially using a series of resistors valued at a power of 2, either divided by 2, divided by 4, or times 2 times 4, all the same, and depends on how many bits you want. That gives you how many bits you want. One thing for that is, imagine if you have a very high bit DAC you want to do with this one. It's going to be a bit tricky because the values you have, you're going to run out of resistor values, essentially, if you think about it. If you start with 1K, and then divided by 2, divided by 2, divided by 2, the last one would be what? 1 ohm or something, which is probably going to be very hard to manufacture or not easy to do. Imagine if you have 20 bits, So, but on this one, regardless of how many bits you add, it's still just that 2 values you need to worry about. And in terms of the components needed, this is essentially 2 times n. This is 1 times n. N is the number of bits. And this is 2 to the n, so exponentially. And this, it's not accurate, but you don't need a lot of components. And this one will be slower because similar to the slope integration, the slope one, it takes the PWM signal, so essentially a lot of cycles to generate one period of the DAC output. Any questions regarding the 4 types of DACs? No question? Okay, cool. Let me see if I have something else to say about this. Okay, cool. So, and we also talked about the different type of arrows on the DACs or ADCs. These arrows shared between them. The first will be the quantization arrows. This is essentially the envoyed arrow that's happens during, like when you mapping a continuous value to a discrete value. What that essentially means is, technically, this should be like a continuous value in between, but since we only have so many bits, that means there is this arrow that can happen on each of the value. The worst case, if it's implemented well, it will be 1/2 amount of the least given bit. And we have the offset arrow. What it means, it's a consistent shift of the transfer curve. So it's possible that everything is shifted to the left or shifted to the right. And chances are these can be relatively easily calibrated by connecting your DAC to a known source inside of the system, so that you calibrate this constant, the constant offset. I realized that in the previous lectures on Tuesday, some of the figures are a little bit confusing, so update the figures. I update the previous slides as well. So the one you see on the class website, that one is also updated. So essentially, it's a shift on the transfer curve. We have the 4-scale arrow, or like the gang arrows. This is essentially a slope shift of the transfer curve. So one way you can have, say the blue one is the ideal one, and goes that way, but on the orange one, which is the actual generated signal, it's just slightly, the slope changes. This is essentially a arrow that's proportional to the steps. So every step you have a proportional amount of arrow, and that accumulates to cause this. You can call them. They call this 4-scale arrow, or like the gang arrow. If you have to have the number, I don't think we test you on this, but on the top bit, that's the 4-scale arrow that you will be expecting. Again, this thing can be calibrated relatively easily with an internal known voltage reference to compare with the generated voltage, so that you can have like a transfer function to shift the curve. We also have the differential nonlinear arrow, nonlinearity arrow. This is essentially the step-sized arrow from the digital output code. So from 000 to 001, from 001 to 010, each, they might have its own like arrows on each bit. So it could be, it might go both directions. It could be a little bit higher than it's supposed to be, or a little bit lower than it's supposed to be. And this is usually like a localized arrow on each of the output step. And then the integral nonlinearity arrow is a overall deviation of the transfer curve from like an ideal straight line. So this is related to the differential nonlinearity, but the differential nonlinearity is a localized arrow bit by bit. This is, you can think of them as like an accumulated arrow from the DNL. But this one also have a, on each of the bit, you could have a INL arrow. It's not necessarily calculated from the top bit, but whatever happens on that bit is essentially what's accumulated from the bottom to that point. So it's possible to have a low interval nonlinearity arrow, but still a pretty bad differential nonlinearity arrow, because the differential nonlinearity arrow can go both ways. And it's possible that they accumulate together at that point to be a low value for the INL, but it still could have a not good differential nonlinearity arrow. Any questions regarding any of these arrow types? Okay, cool. The latter two are, it's going to be more, it's going to be harder to calibrate. The previous three are roughly easier to handle. And recap, these are the topics. We're not going to go through the first half of the lecture's topics. So these are the topics that we went through will be the ones that's being mainly focused on. But on the design question, it's going to be everything together. You will be expecting everything you learned from the previous lecture, previous half of the lecture, to be also on the design question. Make sure you stay, you leave enough time for that, and make sure you don't stuck on one problem for too long. We designed it so that every individual questions can be answered on its own. So, any last minute questions? We good? Okay, cool. Good luck, everyone. We'll post the data sheet after class. If you have any questions, please feel free to come to me.